Hello everyone, welcome to this week's Crunch seminar. Today we have two talks. The first talk is on physics-informed neural networks for blood flow simulation, forward and inverse problem, and is presented by Zhang, who is a PhD candidate at City University of Hong Kong and is expected to graduate in 2026. He was a visiting scholar at Princeton University in 2025. His research interests lie in scientific machine learning for fluid dynamics, computational differential geometry, and geometric deep learning. His current work focuses on blood flow simulation and related computational modeling problems. With this brief introduction, I would like to invite Han to present his work.
Okay, thanks very much, Vivek, for this great introduction. And also thanks for the Professor Kanedakis for inviting me to having these talks at Crunch, which is actually the home of the PINN. And also thanks for everyone to coming here to listen to this talk. Okay, so I will start start my talk. So basically, this talk is about using the PINN to do the blood flow simulations, and it basically will involve the forward simulations of the blood flow and also an inverse problem of it, which we'll assume some like measure data and reconstruct a very physical, meaningful Navier given by the Navier-Stokes equations. Okay. Okay, so the outline of this will be some introduction and the forward problem and also the inverse problem. Within this introduction, we will discuss about the motivations behind these works and also discuss some related works. So the motivation of this work is firstly from the fractional flow reserve, which is kind of like an intrinsic operations, which like you insert a wire inside the vessel lumens with some sensors attached on this wire, so that you could measure the pressure distributions. And after you have the pressure distribution, you could calculate a ratio like the FFR, which is pressure after the stasis over the pressure before it. So if this FFR is relatively low, then that means that this stasis is somewhat serious. That means some treatment should be introduced. However, since this is intrinsic operations, the measurement itself is harmful. So for some like very serious patients, this is like not a safe option. So later, people proposed a computational way for that, which is called quantitative flow ratio. It involves firstly do some segmentations over these measured images and do a geometry reconstruction to obtain the geometry of the vessels. And then they solve for the Navier-Stokes equations over this geometry so that they could have the pressure distributions. Such kind of calculation way could like be free of the intrinsic operation, which is like a much safer choice in some scenarios. Here are some related works that I want to mention. The first one is a Phoenix, which could be used to solve for the Navier-Stokes equation and thus the blood flow simulations. It's basically based on the finite element methods. And another work is is called simvascular. It's just called simvascular. So basically, it's an open source software that includes from the manually labeling of the MRI images to the geometry reconstruction of those segmented mass from those segmented results. And for that geometry, they also involve some meshing. They also include some functionalities for meshings and for the numerical solvings of that geometry of that mesh. But for our works, we are trying to use physics-informed neural networks to solve these Navier-Stokes equations. As here is the home of the PINN, so I will like make this short. To make a PINN works, for example, here we take the Navier-Stokes equations. We should first sample points x, y, z, t from this vessel lumen, so which is a fluid domain omega, and input those coordinates into a neural network and hope this neural network could produce the pressures and velocity for us. So to make these neural networks output the correct results, we hope this P and U satisfies the Navier-Stokes equations. And to do this, we need to convert these equations into residual forms. And these residual forms could then be used as a loss function to train these neural networks. And after it's sufficiently trained, these networks could produce the accurate variables for the desired variables for us. So now we are trying to introduce what the first project, which is the forward simulations of the blood flow in an elastic vessel. Before we try to introduce the models, the equations for each part, we first need to introduce what is arbitrary Lagrangian Euler form. So this arbitrary Lagrangian Euler form is shortly is called the Allen mappings. So this Allen mappings is denoted as AT here, which map could like transform this omega 0, which is the reference domain, into this current domain omega t. And it could map a physical point xt from a reference point x0 by adding a displacement vector functions d. And this d is related to the reference point itself and also the time frame t. So here is a illustration for this movement. So if you have the displacement functions and over this x0, you could calculate the displacement and add the x0 with this d, so you can get the xt, which is current coordinate. So this is basically the Allen mappings that we used to like represent the domain movement. And okay, so we also introduced another variable, which is w, and it describes the speed of the domain movement. And since this d should be defined over the d is actually defined over the reference domain. So to define this w in the current domain, we need a AT inverse to map it back to the current domain. Okay, so the w the movement speed is defined like this. Okay, so after this introduction of these Allen mappings, we give the models of the blood flow. So we describe the blood flow as the incompressible Navier-Stokes equations with some proper boundary condition and initial conditions. The initial condition is like we set we make it start with static state. So that means it equals to 0 at time 0. While for the boundary conditions, the most important part is on the interface. So on the interface, the velocity of the fluid should be equals to the velocity of the solid of this. So the solid part, the structured part is moving. So it will have a moving speed, which we defined just now as this w, and that means this two velocity should equals at this interface. That means the velocity continuity, which we call. And while for the inlet boundary condition, we assume it to be parabolic profile, characterized by some like a velocity function g, the principal velocity function g. Well, for the outlet boundary condition, we use the neutral boundary conditions, which means no stress that prevents the fluid to flow outside.
Hi, can I ask a question about the inflow boundary condition?
Yes.
You're supposed to varying it with the time, right? Because are you following a cardiac cycle or not?
Yes, of course. So that means that here we have the characteristic function g. We have function g here, and this function is related to the time. Yeah, okay. Yes, function of time. Yes.
Okay.
So it's function of x, y, z, and t.
And typically, it's not a parabola; it's a Wormsley profile, but that's fine.
Okay. Okay. Thanks for pointing out that. Okay, so other than this fluid domain part, we also have this stress continuity, which is a model for the interface for the vessel wall. Since we just said that there are some like deforming over the vessel walls, so the models for the vessel wall is described by this stress continuity, and within this stress continuity, the first term is the density multiplied by the volumes and the accelerations. So by the Newton's second law of motion, it's just the force for the movement. While the second term is just the linear elasticity. While the term on the right-hand side is the force that exerted from the fluid. So basically, this stress continuity means the force that the vessel structures use to deform and for the elasticity equals to the force that exerted from the fluid. Okay. So with proper boundary and initial conditions, which means like we start from a static state and we fix the two ends. We could solve for the displacement. We could solve for the displacement functions over the interface. And also because the vessel wall is deforming, it will brings the vessel lumen deforming also. So we use harmonic extensions to extend the D over this interface into this omega 0, the fluid domains. Okay, so that's for the displacement modeling. And then we introduce the networks that we used to solve this problem. The architecture is basically we can see it like we use one networks for the computations of one variables. So for this ND is used for computing the displacement, and this is the only networks for the solid problem. While for the NP and NU is used for computing the pressure and velocity respectively, and it should be governed by the fluid problems. So we firstly look at the fluid problem. It will have some initial and outlet boundary conditions. So we convert everything into the loss functions, and then we will combine them together later. And for the solid parts, for the straight continuity, we have the inlet and we have the boundary conditions, initial conditions, and the harmonic extensions. Again, we convert everything into the residual forms. So we add.
Can I ask a question on the boundary condition? Why the displacement is 0 on the boundary? The boundary partial gamma naught W. Where's that boundary?
Oh yes. So this boundary is the inlet and outlet of this. So you can see here.
Okay.
Yeah, you can see the gamma 0 W is the interface. So the partial of it is just the first the inlet of this geometry and the outlet of this geometry.
Oh, okay.
So
okay.
Yeah.
So you assume that only at the boundaries, not actually. I thought gamma naught W is, as you point out, the green line on the side, but that's not the case. It should not be.
Yes.
Okay. So it's only at the inlet and outlet.
Yes.
Okay. It's a partial. It's a boundary of gamma. Yeah. Okay.
Yes, it's boundary of gamma. Yes, exactly.
Okay. So okay, I got it. Yeah, it's correct. Yeah.
Yeah, I also have a question.
Yes.
Since it's elastic, so your diameter is keep changing in time. So how you take care of that?
Yes. So as we said, as we introduced in this slide, we have the displacement function, right? We have this D.
Okay, but like the input to the network is like has to change the X or
yes, exactly. So we can look at that. That's a very good question. So we can say here, we firstly input this X0 and T into the networks.
Yeah.
So we have the displacement over this X0 at time T, right?
Yes.
And then we could add this D with this X0, so we can get XT, right?
So it's a different coordinate. It's time point.
Yes, it's time. Yeah.
Okay. Thank you. Yeah.
So after that, you add them up. So we have this XT. So this XT is exactly the input for NP and NU. So you can see the velocity and pressure is defined on the omega T, right? And XT is just this point over that omega T. Yeah. So that's a very, very good. Yeah. So thank you. Okay, where am I? Okay, so just now we introduced we're talking about the stress continuity, and we convert everything into the residual forms, and finally we add them up with some proper weightings, so we could trim for this NP and NU with this air fluid, and also this ND with this air solid. So we could so ideally, if we solve for good results, we could like using these two loss functions to trim for the three networks. And we use three independent optimizers for three different networks for independent learning step decay. Okay, so we talk about how we trim those networks exactly. For the fluid part, we just trim alternatively for the NP and NU, which is very trivial, very straightforward thinking. While for the alternations between the fluid part and the solid part, there are something complex. So I will talk about this algorithm step by step. So firstly, we initialize ND with zero initialization. That means initially the ND only output zero vector. That means there is no displacement at the first stage. Okay, so the step 2, we set alpha ns equals to 0. So that means now the air fluid, so because air fluid includes the Navier-Stokes residues and also the boundary initial conditions. Now, since we set the alpha ns, which is waiting for the Navier-Stokes residues to be 0, that means we are only pushing this NP and NU to satisfy the initial and the boundary conditions. So that's the idea is from the what we did in finite element method, because when we working on finite element method, we actually bring the boundary conditions and initial conditioning hardly to replace the variational forms. So which means like those conditions are hardly inserted. However, since here we are trying to use soft constraint pins, so we hope to mimic that patterns as much as possible. So we firstly make the network satisfies boundary and initial conditions first. Okay, so this is the consideration for step 2, and also 3. So after we set alpha ns to be 0, we just optimize it, and then after the first stage, we satisfy the matching conditions. We give Navier-Stokes residual at very small weightings. So we assign a weighting over the alpha ns. And then we gradually increasing this alpha ns so that it could make this network's output satisfy the Navier-Stokes equations gradually. And after this 8 steps, now we are ideally we could solve for the Navier-Stokes over static domains because there's no displacement. And the next thing is how we can the next thing is just we bring the displacement into considerations. So that means we will do the alternations between the displacement between the solid problem and the fluid problem. So we just train the 2 sets of networks alternatively. Okay, so this is a very informative error plot for some one case. So in the first stage, as what we discussed just now, in the first stage, which you can see here, alpha ns is equals to 0. We are only trying to optimize, and we make these optimized networks to satisfy the initial and boundary conditions. So you can see the boundary condition errors are minimized, are decreasing, while the initial conditions are also. While the Navier-Stokes errors are not optimized at all because waiting for it is 0 currently. And then we gradually give it, we first give it a value as very small values and gradually increasing these values. So we can see the Navier-Stokes equations, Navier-Stokes residues are minimized more and more. Or you can see every time when we adjust the alpha ns, there will be an immediate increasing over the boundary condition errors and also initial condition errors. Because now it's like a different weightings between balancing the different terms, so they will have like some jump, but finally it will be minimized to somewhat relatively low errors, which is good. And you can see every time we increasing this weightings, the total errors is also increasing. So after we increase alpha ns into some stage, okay, we can say the Navier-Stokes equations are kind of Navier-Stokes residual errors are kind of converged. So that means, okay, now we need to do the alternations between the solid and fluid. So we just do the alternations. So the dashed black lines indicates the arrows for the fluid part, which in this plot is just as the stress continuity residual arrows. While for the lower part is just the boundary condition arrows and the initial boundary condition, initial condition arrows. So you can see every time the alternation happens, there will be a small jump. But finally, it will converge, and nothing can be again can be further optimized. So that means we reach the convergence. So that's basically the ideas for this work. And here we present some results. So these animations, maybe you can hardly find a propagation phenomenon. That may be because like we use in a boundary condition like this, which is just a cosine function, which is very smooth, so that you cannot observe the propagation. But later we will present a result with a good propagation. Here is the quantitative results. So each column represents the relative errors given that specific mesh resolutions. And each row is corresponding to a time step. Well, you can see in this entry, the relative error is 0. That means this entry, the corresponding mesh of this entry and the time step is treated as a ground truth. So you can see for this ground truth, we take approximately 70,000 to compute it. Well, you can see for the rectangle results, and our results are comparable to the results by the corresponding finite element methods, but the computational time is like slightly fewer compared to the finite element method. Okay, we also take a self-ablation to determine the optimal configurations for the networks that we used for the PINN. Here we take the NU, which is computed for the velocity, fluid velocity, as an example. So according to the results illustrated by those plots, we could say, okay, depth of curve should be optimal, and if we even increasing this depth, the time consumed we're also increasing, while the results didn't really improve a lot. But we could say, okay, a width of 30 should be the optimal in this case. So that's just the configuration that we choose in our implementations. Here is another example with a slightly more complex geometries, which is a vessel geometry with a plug. So according to the same comparison logic, we could say, okay, our results actually get slightly better relative errors, while we actually saved a lot of times comparing to the corresponding finite element mesh. I think this is because like PINN is kind of like meshless, and if we use finite element method, specifically for the interface parts of the plug and the vessel geometry, there are some like sharp edges, which means like more discretizations should be needed over there. So I think that's the reason of like this better results. We also investigated how different size of the plug could influence the fluid dynamics and also the pressure assigned over the plugs. So as we can see from these two plots, a larger plug will make the pressure that assigned over the green point, which is the peak of the plug. The pressure will increasing quadratically as the increasing of the plug size, while the fluid velocity at the red point will decreasing also kind of quadratic, not strictly, but kind of like quadratic as the increasing of the plug size. Okay, here we present another example which could observe some propagation phenomena. So you can see we take a much sharper inlet boundary conditions, and this enables the propagation phenomena behaves. Okay, so that's for the forward problem part. Sorry, let me drink some water. Okay, so let's come to the inverse problem, which I think is much more interesting than just than the previous, just trivially forward simulation one. So the inverse problem is the problem of the inverse problem is something like this. Firstly, we will assume some matter data. So this matter data only gives us some noisy velocities, and maybe those velocities didn't really satisfy the Navier-Stokes equations. So what we want to do is to like find another modeled velocity u. So this matter data is indicated by this u tilde. So what we are interested in is this u. So we hope this u, of course, to be similar to the u tilde as much as possible. And this u, because of physics, we hope it should be like satisfy the incompressible Navier-Stokes equations with some boundary conditions.
And I have a question.
Yes.
What kind of measurements? The only measurements I can think of is that can give you velocity will be PIV, but you don't do PIV in blood flow.
I think flow MRI or like a Doppler ultrasound could give some information about
fMRI.
velocity.
So fMRI in small arteries, maybe, yeah.
Yeah, okay. The flow MRI, yes.
Yeah. Okay.
Yeah. Yes. So okay. So what we hope to do is to have this U to be approximate to approximate the U tilde as much as possible, and this U of course is need to satisfy the constraint that is modeled by the Navier-Stokes equations. And over here, what we need to pay attention to is like the omega is also undetermined. So that means omega is the factor that we need to optimize. As you can see in the optimization problem formulation, this omega is also need to be optimized. However, optimized omega is like somewhat complex and not that straightforward in terms of the representations. So we hope to, we're using a mapping approach. Yeah, we're using a mapping approach. So the benefit of using the mapping approach is like if we control the properties of the mapping F, we could actually control the property of this omega. So that's to say, if we use this mapping F to be like a topology preserving mapping, then this like prior domain omega 0 should then have the same topology of this omega. So that means if we have some like specific organs, some specific parts of the vascular segments, then we could have an initial guess, and we optimize for the mapping F and benefit from the initial guess. The resulted domain should have the same topologies. So that is something we can benefit from some prior knowledges. Okay, so by using this template domain, this template domain omega 0, we're using mapping F to deform it so that we can get the omega. So now we could replace every omega into this F omega 0, and also the boundaries are also mapped correspondingly. So now the problem is reformulated. We are optimized over this mapping F, and all those omegas are represented by a template domain omega 0 and an optimizable mapping F. So now optimized for the omega becomes like much more simpler, as there are many structures to optimize for the mappings. But also this problem is still like somewhat complex because it involves multiple factors. So what we did here is trying to split the complex total problem into two subproblems, which is kind of similar to the forward part, so forward one, but we have a reformulation for the geometry part. So for the splitted problems, it's split into the fluid subproblem and the geometry subproblem. In terms of the fluid subproblem, it's just trivially it's almost the same problems as the as the original problem, but the mapping F here is fixed. So what that's to say, we are only optimized for the innet boundary condition G, and also solve for the velocity U. So that's for the fluid subproblem. And while for the geometry subproblem, we're trying to like reformulate the geometry subproblem into a registration problem. So that's to say, we hope the U tilde, we hope the model, the velocity U, to be similar to the U tilde as much as possible. So we're trying to use a registration mapping to do this. So that, like to say, we use this mapping C. We call it a correction mapping. We use this mapping C to deform this velocity U to be close to U tilde as much as possible. And this C, in this case, could be considered as a domain gradient. So record just maybe you could see this. This here is C. Here the mapping is C, but here this domain is F. So that means F is kind of like the accumulated correction mappings. Okay, so you can see every time when we do so of course we do the alternations between the fluid subproblem and the geometry subproblem, and every time we do the alternations for a new for the mapping F in next iteration, we will have a C inverse composite over it to obtain the new F. Okay, so to have this, so just now we said, okay, this mapping C should have some like topology preserving some properties. So how can we make that? We now have this quasi-conformal geometry theories. So in terms of this series, important thing is just the definitions of the quasi-conformal mappings. So basically, a quasi-conformal mappings you could think is like a topology preserving mappings that, like the example we showed in here, this omega 0 could have the same topology of the omega. If this F mapping F is like topology preserving, or we can see it's quasi-conformal. So if a mapping is quasi-conformal, so how can we determine if a mapping is quasi-conformal? That means for a mapping F, we could using these differential equations to calculate for the Beltrami coefficient, which is just this mu. So you can see this is somewhat a simple differential equations. So that means we could actually compute for the Beltrami coefficients mu. And if this mu is strictly less than 1, then we could say, okay, this mapping F is quasi-conformal, and by the property of quasi-conformal, it's also topology preserving. And the topology preserving basically means homomorphic. It means like it's a homomorphism, but not a diffeomorphism. But diffeomorphism means like a smooth diffeomorphism, smooth homomorphism. So that means we'd better also make F to be smooth because we want to control it to be like a visually pleasing, or like because we are using some images. If the mapping is very like sharp, then the deformation of the images will bring in some like interpolation blurs. So we are trying to also make this F to be smooth, so that it could be a diffeomorphic. And also later we will have a proof that need F to be diffeomorphism. That means we need to enforce the smoothness of the mapping F. So that makes the conversion of the residual forms and the loss functions. For the fluid subproblem, it's just very trivial. It's just very trivial. So we convert everything to residual forms. So we have the loss for the fluid part. But for the geometry part, firstly we have the registration, and we have the penalty over the Beltrami coefficients to make it less than 1. And we also have the Laplacian of C to be regularized to make the correction mapping C to be smooth. And so this is the overlook of the whole algorithm. So it should be more clear to bring a concept to you on this algorithm. Firstly, we start with some template mask, and we could sample some coordinates over this the domain indicated by this template mask, and we input those coordinates into the PINN network, and it could ideally it could produce the velocity and pressure. And to make this work, we should train this PINN by using this fluid loss. So after we get a sufficiently trained PINN, we could have this correct velocity for the current iterations. So we could have this resampled flow image. And we wanted this resampled flow image to be similar to this U2, to this measured noisy flow image. So as we said just now, we use the registration mapping to do this. So we have U composes CI. We hope it to be as close to the U2 as possible. So to produce this CI, we have it here. So we use the UNet, which takes the U as the input and produce a CI. So by optimizing this UNet, we are actually optimizing for this CI. So that makes this procedure optimizable. And this CI, other than warping these mappings, it could also warp this template mask to be a more accurate mask, which could be used for next iterations. So we have this M omega I plus 1 equals to the M omega I composite CI. Okay. So we go this procedures iteratively, and finally we could get, if we could get a convergency, then we could get a solution. So here is proof for this. Because the whole problem is to optimize for the inner boundary condition and also the domain omega. But we actually splitted this original total problem into 2 subproblems. So this theory is to say, okay, by solving alternatively of these 2 splitted subproblems, if the final solutions converge to some limit, then this limit is actually a partial and a local minimizer of the original total problems. So here, this one is the original total problems, and this UN and FN is solved alternative by alternations between the splitted subproblems. Okay, so this is the theory that we derived to support the validations of such a splitting. Here are some experimental results, which we take firstly take like simple geometries. We compared our results with some conventional denoisy method. So you can see our methods really like preserve a good smoothness compared to the conventional methods. While for the quantitative results, we also achieve some like better results than the others. However, for the very like low noise, like the somewhat sometimes it may be because the noise is very light, so it's like common to for the denoising methods to behave good. So yeah, and we tested also our method on like a somewhat more complex geometry. So we also compared them with conventional methods, conventional denoising methods. So you can see, or if we use somewhat very high noise, the conventional methods just smooth out everything, and of course it doesn't satisfy the Navier Stokes equations, while ours illustrate a good results, good visual results. And we're also trying to like plot out the streamlines from those reconstructed images. Well, this is for the low noise, while you can see the conventional methods also behave somewhat okay. While for the high noise, that they are just not usable, while our methods could still like brings out reasonable streamlines. While in terms of the quantitative results, ours achieves the best. Here are the reference for these two papers, and that's all for the PINN related works. So if you have any questions.
Hi, Hen. So this is Nikhil. I'm a PhD student working with Professor Karninatis. I have I have one question. If you go to slide 46, when you're showing the architecture overview, in this you are predicting U and P, right? So that P is a pressure, right?
Yes.
Do you have any comment like how well or like what's the accuracy of that pressure you are estimating with?
Within this work, I didn't test it for the pressure part because I just didn't tested it because mostly I assume the given data is a velocity part.
Yes, but I was just wondering, I was trying to estimate pressure, so because those measurements are not how, like you usually don't know them. So I was just wondering your method might be interesting to estimate that as well.
Okay, I think that's a very interesting part. I will do that after.
And also you showed that measurement set after that those are simulations, right? If I understood right, like you are showing on slide 52 the aorta, and those are simulations, right? They are not 50. From like that one and this one. Yeah, this is simulations, right?
Yes, it's simulated. Yes.
Okay, and so do you have any data from like 4D flow MRI, or like have you compared it with that? Like because you need the noisy measurement. I was just wondering if you use that.
Yes, exactly. So so you are very good question. I think firstly, in current stage, I don't have the real 4D flow MRI, but because this is kind of like proof of concept, we're trying to build up the first models, and later we are currently actually trying to extend it to a 3D. Trying to extend it to a 3D case, and also with some like fluid structure interactions. And for that part, we are collaborated with a professor from Emory. I think, we are collaborated with Professor Alessandro of Nazani. So he said he will have some data over that. So I think later we could really test on those real data, but not for current.
Okay, thank you. It's nice. Thanks.
That's fine. Thank you for your questions. Thanks.
Hi, I had a clarification regarding the architecture. Could you go back to slide 46?
Yeah, 46.
Yeah. So two clarifications. First, are you training the PINN and the UNet jointly, or how is the training being done here?
No, I'm not trying to train them joint. I mean, I don't try to train them simultaneously. I try to train them alternatively. So that's to say, I firstly, so for training the PINN, okay, for training the PINN, I assume the mapping to be fixed. That means here I'm not trying to optimize for the UNet. Right.
Okay.
Do you understand? Okay.
Yeah.
So after the PINN is sufficiently trained, we could actually produce a resampled image U, right?
Right.
Okay, so now the green part is finished. So we don't care about the green part. We just train for the blue part. So now we fix the velocity flow, the resampled flow images, and do the registration process. So that's where we train the UNet. So that means in that part, we've actually kind of fixed the PINN, but only train for UNet. So that means we train the two problems alternatively.
Okay. So do you have some predefined number of iterations that you perform for each of the models?
Yes, actually. I basically I do the empirical test to determine the specific epochs that for each subproblems. Yeah.
Got it. Okay. And one last question. So when you get this mapping, how do you concatenate, or like how do you blend it with your base geometry? Like, is it some element-wise product, or what is the operation that you're doing exactly here?
I'm sorry, I don't exactly understand your questions.
Right.
Do you mean I compare the results of the solved mask to the ground truth mask, or?
Yeah, so I'm asking, how do you generate the mask with the mapping as input? Like, what is the operation there?
You mean
let me try to annotate here. Yeah, I mean, like, what are you doing here exactly?
Okay, so here I'm trying to using this mapping to spatially transform this m omega I. So that means if you're using PyTorch, you could using the function grid simple.
Okay.
Okay, so that's just to say, okay, you're using a mapping to transform the
Got it. Okay.
m omega I. Yeah.
Okay. Thank you.
Yeah, welcome. Thanks for the questions.
Hello, my name is
Yeah.
Zhang. I'm a PhD student at Crunch Group. I have a quick question about the flow structure interaction problems you mentioned,
Yes.
the training iteration. So you've done the yeah, thanks. If you could go back to the slide. Yes, so I see that at line 9 to line 12, you are iteratively optimize the solid fluid problem. What would happen if you train them simultaneously? Is there any motivation that you split these things and do optimize one model at a time?
So the very straightforward answer is like if you train them simultaneously, that will be. I'm not sure if I'm not sure if it will lead to a convergence, but empirically, I try to like do them alternatively. Because it's something like this. For a GAN, basically you have the adversarial, and the generator. Basically, when they train for the GAN, they do the alternatively training. So I just borrow their ideas. So here I'm also trying to do the training for the two problems alternatively. If you train them separate simultaneously, that means I think it should be somewhat challenging because
so viewing these kinds of two models as the generator and discriminator in some sense.
Yes.
I see.
I mean, kind of, not exactly. It's not really trying to talk with. I mean, it's not really want to like adversarial, right? They're trying to collaborate, but I mean,
I see.
Even though you do them simultaneously, it's kind of like alternative. But here, what I'm trying to do is like my idea is like, okay, I fix a domain and I make this domain. I make my model could solve for the Navier Stokes over this fixed movement domain. And then after this Navier-Stokes solved over that domain movement, I then optimize for better movement given that Navier-Stokes.
Okay. Is there any analog to these kinds of iterations in traditional numerical methods like finite element? I mean, solve for the solid and then solve for the fluid, or it's just something you come up with this good idea and implement it?
Yeah, I think there are both. So there are some works that simultaneously solve the two problems. They basically, I think they embedded some part. They embedded the one into the other, so they could solve them simultaneously. But I don't know exactly how they do that. But also for the paper that I read, they just solve them like alternatively.
I see. Thank you very much.
Yeah, thanks for the questions.
Hi, Han. I have a question. Can you go to few slides behind where you showed the evolution of the lost? Yeah, this slide, precisely.
Yes.
So I was wondering for the Navier-Stokes residue, the second row, the numbers look a bit high. Are you training on a normalized PD or an unnormalized PD?
Sorry, what do you mean by normalized?
Oh, okay, just a second.
Why your values are not 10 to the -3? Why is it 10 to the 6, 10 to the 7?
Okay. I think that's because I'm not using the dimensionless formulations.
Dimensionless form, okay.
So that means I'm actually using the CMS unit. So I think that's the reason that I make these arrows so big.
If you non-dimensionalize the equations and do the scaling and rescaling correctly, you might be able to get better results. Just a suggestion, but yeah, great work. Thank you.
Yeah, thank you.
But this type of alternating between physics has been done also by others. But even in our group, Chancy, I don't know Chancy is attending, but in her paper, she trained this system like for bioreactors, something like that. Chancy, are you there? No. Anyway, it's very similar. So it's not very. It makes a lot of sense for multi-physics problems to do that. Yeah.
Cool. Yeah, thank you.
Yeah, one last question. So I think in the next, could you go to the next slide? Where you were showing I think the algorithm where you summarize how you do the training. Yeah. So in this, like the first for loop that you have where you're iterating from 1 to 5, like is that something that you have empirically seen? Like, because if you're only going up till 5, the alpha of Navier-Stokes can be at max 10 power -3, right? So like how do you determine that? Because 10 power -3 still, you're not giving enough significance to the Navier-Stokes corresponding loss, if I understand correctly.
According to my results, it should be sufficient. So in terms of how can I determine these epochs, I mean, it lasted for like 5 epochs. I just do them like empirically. Because if I even increase in alpha and S, then the boundary initial conditions will be broken.
Right. Okay. Got it.
Yeah.
Real quick, it has to do with what Vivek asked, the questions that Vivek asked, which is like what's the residuals are very large. It's because the residuals are not order 1. So that's why.
Yeah.
Right. Okay.
Yeah, exactly.
Makes sense.
So alpha has to be, yeah. Okay.
Yeah.
You have more to tell us, right? So,
yes.
Okay, so maybe you can proceed with that.
Okay, thank you. So I will be like very excited to share this one with you. So because the previous ones is only with like PINNs, but this one is kind of like with like operational learnings. So what we want to achieve is to do the whole body vessel networks blood flow simulations. But if we treat the whole body vessel solutions of the Navier-Stokes, it will like be a huge task even for one case. So if we want to train the operator to solve for the whole body at a single time, then preparing for the dataset is extremely consuming. So that means like it's like not that much doable. But here, an idea of this could be like for the whole body vessel networks, we could actually decompose it with this into some similar units. So a very straightforward idea is to like decompose it into like a straight segment. But here, what we are trying to do is to like decompose it into some multiple bifurcations, and we will have a reason for this. So firstly, by this decomposition, also we are using 1D Navier-Stokes equations and in the dimensionless forms. So that means every geometry should be similar. Every segment is just like, in the domain of 0 to 1, while the real length, characteristic length is the input parameters of the operator networks. And other than those parameters, what we need to have is the boundary conditions, because the initial conditions should be given. So that means the initial conditions for each unit should be known. So we don't need to care about that. But for the boundary and initial boundary conditions for the inlet and outlet, for the outlet, we benefit from this paper. What does that mean? We could actually, if we're using the Winksow outlet boundary conditions, we actually could do this. That's to say, we could simplify this this vessel 1 with these 3-element Winksow boundary conditions into this 0-dimensional models, and we also do this for the vessel 2. And then this by using this one, and then we could actually convert this one into this one, which is one single segment with a new updated Winksow parameters. So that means for every single segment, we could have the outlet boundary conditions. Okay, well, for the inlet boundary conditions, it's not that straightforward to have, because we only have the conjunction conditions for the inlet of the children units. Even though like I mean, firstly we could think about a single segment. So a single segment, because we only have this conjunction condition, we don't really know what's the flux at the inlet of the segment 2. Because what this is only, we don't have explicit formulations for this. But if we're using a bifurcation, we don't need to really compute for the we don't really need the explicit formulations for the splitting of the flux. That's to say, okay, if we solve for the bifurcation 1, which is the black part, then we know the flux at each point. So that means at the red points, we also the flux over there. And for the green points is also. So that means for the bifurcation 2, we could now actually have this inlet flux. So that means for the children's bifurcation units, we have both the inlet boundary condition and also the outlet boundary condition. So that means if we have a good enough operator networks, we input all those things, and the operator networks can immediately output the solutions over that bifurcation unit. And also, of course, because it's like bifurcation 1 and bifurcation 2 will have some overlaps. So there are actually some discontinuities. So we will have some towards iterations to like some method from the domain decompositions with some overlapping domains. We have some like iterations method to like correct those discontinuities. And finally, from our experiments, we have some good results compared to the ground truth. So this work is collaborated with Princeton University. While there are some works I just briefly mentioned because the limit of the time, the geodesic learning, which we are trying to use a quasi-conformal mapping to deform the deformable convolution over the manifold. And the main part, the most interesting part is like we have the theory that states that such kind of quasi-conformal convolution could generalize a very large set of convolution over the manifold. I mean, in the spatial sense, not in the like some spectral sense, not something like that, just in the spatial sense. And some ongoing things, like I said just now, we are trying to extend this inverse Navier-Stokes equations into like inverse fluid structure interactions, which is 3D and involves time evaluations and with some elastic boundary or vessel walls. And also, I'm trying to use some to do some like conventional finite element methods. Here we are trying to solve for the magneto-hydrodynamics equations. And we hope to derive a finite element method that could preserve both the divergence B and the divergence U. So that's all for the works that I want to present here. Thank you.
Thank you, Han. Do we have any more questions for Han? If not, I would like to thank Han again for staying up late and taking his time to present his work. It was very interesting. Thank you. And with that, maybe we could move on to the next talk.
Okay, so thanks for everyone.
Thank you. Maybe Professor Howe, I think you're there. Can you please try sharing your screen? Hi.
Okay, good. Let me.
Yeah.
Can you see my screen?
Yes, I can. This is perfect. So I will introduce you. I'll introduce the speakers, and then after that you could start. Is that okay?
Yeah. So let me make sure my other people are here. So let me Zikui is here. Yeah, Zikui is here, and Zhenlong is here. Okay, I see it. Okay.
All right. So moving to the next talk, we have 3 speakers presenting the work ZENN, a thermodynamics-inspired computational framework, presented by Professor Wenrui Hao, Zikui Liu, and Zhenlong Li. Professor Hao is a professor of mathematics at Penn State and director of Center for Mathematical Biology. His research focuses on computational modeling, scientific computing, and machine learning for complex biological and biomedical systems. Professor Liu joined Penn State in 1999 and coined the term materials genome in 2002. He has served as editor-in-chief of the CALPHAD journal since 2000. Professor Liu developed zentropy theory and the theory of cross phenomena and created new journal Zentropy in 2025. Professor Zhenlong Li is an associate professor of geography at Penn State and director of Geoinformation and Big Data Research Laboratory. His research centers on geospatial big data analytics, spatial computing, geo-AI, and autonomous GIS. With this brief introduction of the authors, I introduce you to present your work. Thank you.
Okay, thank you very much, Vivek. And also thank George for invitation for this presentation. And so this is a very disciplinary collaboration and recent work. So I invite my colleague Zikui and Zhenlong can also present with me together. So this is ZENN is based on Zentropy. You will hear later. So what's the Zentropy? And this is most of today's talk is based on our recent published PNAS paper, and you can find from this link, and you can find the paper, and also you can play with the code on this is the QR code. Anyway, so let me start. What's the Zentropy and what's the ZENN work for? So most of the case, and we want to answer a question which is data heterogeneity. So this is quite important. Is also a challenge of the data heterogeneity, which is increasingly common as a data set collect from the different multiple data set. Okay, so when you let me see. Okay. So I will briefly review how the entropy will used in the physics and the information theory, and why the current machine learning model, which is based on entropy, is cannot apply to this heterogeneous data set directly, because this is a simplified version, and you always the assumption, big assumption is you have a one unified data set. So we will present our work and extend these ideas to demonstrate effectiveness and data set, and also apply to the real application is extend to the graph neural network and the geo application, which is presented by Zhenlong. Okay, so then what's the data heterogeneity? So this commonly used in current machine learning. One of the most persistent challenge is the data heterogeneity. In many applications, we collect the data is not only from a single controlled experiment, right? So instead, we integrate the data from the different sensors, different laboratories, different platform, and each of them is have different noise and have different biases, right? So how you have these different resources, merge them together, and then you should consider this, otherwise your model prediction is not very accurate. Okay, so probably this is all the formal definition is not really understand what's the data heterogeneity. So let me give you one example, right? So let's see. We want to use this as a simple example to demonstrate the idea. Suppose we have 4 different people, right? So we want to draw a cat, is maybe myself, Zikui, Zhenlong, or maybe George, right? So we are asked to provide the image of a cat, and we all produce the data about the same object, which is a cat. But the way how do we present, how do we draw is different, right? So it's because some of us can draw a cat, but most of our drawing abilities are quite different. Some of them are very good. You have the strong artistic skills, but some of them is not really good at drawing. Okay, so then you can see even draw the same object, we could have the very different. Some of them is very realistic, some of them are very abstract, right? And you may say I never draw because I'm not good at drawing. So how about I just use my phone to take the pictures, right? So then you have the same issue. So you have take the picture of the cat, then the image could be use different phones, different cameras, and you use the different lighting conditions or different angles. So all the end. So we should have a very different data set, but the whole data set is labeled as a cat, right? So you have the different drawing styles, you have different camera qualities and the different resolution and the noise level. And from machine learning point of view, so this is called a heterogeneous data set because the different data points cannot come from the single consistent distribution. Instead, so this is a kind of mixed level and mixed noise level and different data generation process. So this is exactly the type of hidden structures we should consider in the machine learning because you have the data is from the different resources. Okay, another example is I want to from my own research. My research is part of biomedical machine learning. So you can see the many clinical setup, and we collect the patient data from the different multiple hospital rather than the one single institution, right? So each hospital may have different medical devices, and could be imaging machine, could be laboratory system, it could be different, right? So for instance, if you take the MRI and the CT scans from the different manufacturers, so they can produce the image at the different resolution and the construct levels, and also the noise is quite different. Even you say, oh, I don't take the imaging data, but you take the blood work, so this is the blood test measurement could be different. You need to calibrate, and laboratory procedure could be very different. So in order to integrate all the patient data across the hospital, we cannot really combine them simply. So there is one term actually is called the data harmonization. This is most of people doing this is based on, okay, you have graduate student or you have research scientist, then you can merge everything together. You can do the denoise and everything. Okay, so this is the whole idea is can we do from machine learning point of view? So can we do everything is built in the machine learning framework? Okay, so this is I'll give you another example. This is I think is if you do the machine learning, this is pretty standard data set is the CIFAR 10 and the CIFAR 100, and each class is labeled, right? CIFAR 10 you have 10 classes, CIFAR 100 you have 100 classes, but the data collected is from the different photographers and the different cameras and the lighting condition, the environment. This is different, but we all put them together is called one data set, right? So this is a data set is very complex and also the multi-model. Okay, so how can we put this heterogeneous data consideration into our image classification process? So let's look at what's the traditional classification process. So what we are doing is, I think most of the people this is the so-called cross entropy, right? So how do you do is, okay, let's see we have a model. So this model could be RASNet, or could be VIT, which is a state-of-art model for the CIFAR 10 and CIFAR 100. And let's just see there is 3 classes, right? So you have dog, bird, and cat, right? 3 classes. You use whatever model, you can predict the probability for each class. But you look at that, you have labeled data. So for instance, if this image is a dog, I just have dog is 1, others are 0, so you have vector. And after that, you combine, look at what's the cross entropy. So this is you have 1i is your label, and the pi is the probability from your whatever model you have. Then you want to maximize the cross entropy. Eventually, you can train your model. So this is the M is J is from the different samples that you can do that. So you can see from here, there is nothing deal with, okay, if you input data is from the different resources or different, they have different property, how can you incorporate into the learning process? There is nothing we are talking about this part, right? So that means this is the whole entropy, cross entropy loss is designed for only one unique concentrated data set, right? How do you do this? So then let's take a look at what does entropy means, right? So let me talk about this roughly. Then I give this to my colleague Zikui, because who is an expert in entropy. So this is essentially from here you can see this is from the very beginning. The entropy essentially is from the physics, Gibbs entropy. Eventually you go to the Shannon entropy and apply to the information theory. So they have the different formulas. And but if you look at this one, it's actually start with heat, and we start with the microstates, and eventually you have the different configuration. So this is the quantum system. Eventually you move to the information theory. So if you compare 2 of them, is quite similarly. The PK is for the different probability for different state. Then you have the right hand side. Then you have the Shannon entropy over here. So because we look at the different PK, and you have all the PK summation of the PK, the probability equals 1. Then you have the 0 order movement, or people sometimes is called normalization. Then you have first order. That means okay, PK times EK, which is mean equals is also a constant. Okay, so I think let me give this to screen to Zikui, so Zikui can talk more about what's the entropy. Then how we incorporate the different resources, the data into the entropy, which is called the entropy. Okay, Zikui, are you there? So do you want to share your screen?
Can you see me sharing?
Yeah, go ahead.
Okay. So as we mentioned about this different entropy, that's how entropy started, and go from the heat to the microstate configuration.
Okay, can you share your screen?
You see it now, right?
No.
Yeah, I share the screen.
Yeah, I can see the heat to microstates configurations.
Yeah.
Is that the screen?
You need to move the 2 windows there. You have 2 windows. You move another window in your case.
Go ahead.
So now this side is that you have this keeps the statistics mechanics, and then you have this Shannon's one, as we mentioned. But the question is that each configuration may also has entropy inside. Okay, so how should that be considered? As when you showed the cats, right? Each cat is different. Okay, and then from the quantum mechanics point of view, we can calculate Gauss configuration entropy. So how does that play a role? And now we also know that if we take a ground state, there's one configuration, but you have many configurations together. How do you put them together into the framework, which is not covered by the entropy we have seen so far? So what it means is that now we have to put 2 configurations together. This is the information of the Shannon and Gibbs. So the green part here is basically each configuration has entropy. What it means is that if we think about the entropy of the system, we have to include the entropy of each configuration too. Okay. So that means we have to add 1 term into the total entropy. So the entropy would be more accurate for the system. All right. So So if you go back there, what it means is that if you look at what the Gibbs entropy or von Neumann entropy or Shannon entropy, they take these configurations, but each configuration has no entropy in their system. Okay? So you don't have entropy there. And then you get this P log P term. And then you have the coarse entropy as when we showed. However, we're not taking the configuration with zero entropy because each cat has its own entropy inside, right? So that means we have to basically are grouping them now. We're kind of coarse graining. We coarse grain the very pure state configuration into kind of intermediate configurations, like quantum mechanics. That's one of the things we do in the DFT. So those configurations, each of them has entropy because they have the pure state configuration inside each of them. Again, take that cat as the example. That means now if we want to talk about the entropy of the system, we have to talk about the Q log Q now because it's a new set of configurations, and then add the two together. So this basically is entropy. Okay, so what it means is that the entropy is Z plus entropy. So we have this P log P because all entropy is P log P. Okay, so basically to the different level of coarse graining, so each level of configuration at different level also has entropy. Okay, in that sense, Z is basically is a partition function. So that's why we have Z as the entropy. So if you write the entropy in the function of in the partition function, then you get this has to be Fk. Okay, basically now you have E. If you take the classical one like Gibbs and Shannon, you have E here as energy has no entropy. So F is basically E minus Tsk. So you get this each configuration entropy into consideration. So when we talk about S1, it's actually equivalent if each configuration has no entropy. That means if each cat is identical, okay, each dog is identical, then they have no internal entropy anymore, and then you go back to the Shannon entropy because that's Sk equal to 0. Okay, and when we present this kind of work to the DFT people, Jean Perdue, as you may know, his team created this GGA for the quantum mechanics calculations, and he pointed out that it's simplified quantum statistical mechanics. So it takes quantum entropy, add into the statistical entropy together. That means we can get a much better prediction of the complexity of the system. Okay, so I think let's go back to Wenrui. Its idea is that how we put this equation, how we change previously this term only, right? Now we add this term, how we do the computational mathematics put in the neural network. Wenrui, it goes back to you.
I thought you will talk about this part.
Let's talk about it. It's coarse entropy now. Okay, that's a very interesting one. That's the key is that how do we put a two entropy term into the machine learning framework?
Yeah.
That's next one, right?
Yeah. Okay. So this is
That's
so
right.
from here you can see if I put everything in the simple, if I Sk equals 0, you can essentially go back to the cross entropy. So this is the PK, everything is the same, right? So the whole point over here is we introduce the Sk for different configuration, which tell you what's the noise, right? So if you have a equilibrium state, so this is the Sk equals 0, you can just use the cross entropy. But from the different data set, you may have the different SKs. This is the whole point. We need to learn, not only learn the PK, but also learn the SK for the different data set. But because we include the SK additional variable, is before we have the two of the constraint. One is summation of the PK equals 1, which is the normalization constraint, or you can call it the 0 order momentum order is equals 1. So this is the first order momentum equals is mean equals something. We need to include additional because we introduce this actually is quite straightforward. But then we can just have the PK and the SK square. So this is the second order moment equals a constant. Okay, so once you have this is the setup, so this is the you can see is you have an optimization problem, but you also have some different constraint is the zero order movement, first order movement, second order movement. Then you can combine them to solve. This is similar to how we derive the cross entropy similarly. So then you can derive what's the PK. So from here you can see the PK depends on two of these, right? So it's not only for EK. So before is you can think about is for the cross entropy you only have FK and the SK equals 0. So this is essentially you only include the EK component. But right now we include two of them. One is EK, one is SK, right? So this is from here you can see. So this is what we have for different component, the probabilities. This is the PK. How you compute. So this is not only depends on one of them. So you have two of them. Then you have the normal temperature T to distinguish the different data set. But over here, because we include the one of the additional constraint from here, so that's you can see the second order constraint. So this is the additional, this is the new one. Okay, so this is PKSK, this is also new from the loss function. Then you have additional constraint over here. Because this everything is through the Lagrange multiplier, right? So you put a Lagrange multiplier lambda 1, lambda 2, lambda 3, right? So this is essentially one of the Lagrange multiplier is called the temperature, right? So this is normally what we introduced in the cross entropy. But because we include another additional one, we include another quantity is gamma over here, right? So this is the gamma is actually the quantify fluctuation of intrinsic entropy among the configurations. But what's the physical meaning of this gamma is not very clear. So this we just derive this from the mathematical point of view, and we can fit the gamma and the T through the data. Okay. Okay, so then from here you can easily to see what we have. We have the different of this is you have the different configuration 1 and the configuration 2 and the configuration K. So this is the whole big picture. So you have different configuration built into your neural network, and for each of the neural network you should also have two parts. One is for EK, one is for SK. So once you compute the EK and the SK, you can have FK, which is you compute the probability. So this is not so if you look at the formulation is more complicated than cross entropy because you introduce each of them, because in cross entropy case SK equals 0 and the FK equals EK, so they are the same. So it's much simpler. But because we need to incorporate the different SK for different configuration, we need to include both of them. Okay, I think that's all we have for the cross entropy. Zikui, you want to take this part here, or you want me to present?
You can continue.
Okay, so the first example we want to compute is, okay, so over here, so temperature is a known variable. Let's learn how you learn the bifurcation. So how you learn the bifurcation, so you have the given, so this is the energy landscape, and we want to find where is the critical points. Okay, so most of the case, there are many existing work people using different method, and it's both of them. I think it's very high quality papers published, but underlying they are using cross entropy. Okay, when you learn the cross entropy, actually you can see the bifurcation when they cannot learn the accurate bifurcation diagram. So that's we come to how we learn from our case. So from here you can see we use both neural network to approximate EK and SK. So you have two set of parameter, and the theta E case component and the theta S case component. X is input and the T is also input. Then from here we can use the KL divergence is our loss function to find what's the bifurcation point. So the first we want to learn for different. So this is our artificial data. So we let's see. You have the f of xt is given like this, right? So you will see there is a bifurcation diagram. You can see this is a different bifurcation diagram. You can have the transition for the different. What we have is for different t. We first sample for x. Then you can use this one to compute. And essentially, you can use the t equals 0.5, t equals 1, t equals 1.5 to train your data. So this is t equals 2, this kind of prediction. And so from here, you can easily to tell. So several notation here is so first of all, so how you find the bifurcation point. So the bifurcation point essentially tell you if you take the df dx equals 0, then you can get a bifurcation. So if you have the different so traditional method ZENN, you can see is because you only fit the f. When you take the derivative, actually you see a lot of oscillation, right? So then actually is pretty stable after you do the discrete differentiation. And if you take the second order derivative, and then is even more stable. So you can see it's a traditional method. You have a lot of oscillation because when we train the data, so you only give a function value f of xt, but you didn't prescribe any derivative information. So in this case, ZENN is quite stable. So you can learn this bifurcation pretty well. And the second one is, I think this is from the material science, is really from Zikui's expertise. And Zikui, so how about you talk about this part, and then I come back for imaging classification.
Okay, let's do that. And so the idea is, I didn't share my screen.
You need to share.
I didn't share my screen. Okay, now the iron 3 platinum is a very interesting material. And
hi, Professor Liu. Could you please go to slide? Thank you.
Yeah. So iron 3 platinum is INVA. INVA means the volume decrease with temperature. It's called negative sum expansion. Okay. So what it means is that usually we say when temperature increases, volume increase, right? But for INVA, at some temperature range, the volume will decrease when temperature goes up. Okay, that has a critical point as when we mentioned. So what it means is that we need to get the homogeneous immediate constraint because each configuration must be stable. Okay, so I have to get this convexity. So second derivative must be positive. That's not constraint. I put it here. Each configuration must be stable. So, but it's a real a function here to make sure the second derivative is positive. Okay, and then we can calculate the first derivative, gradient, as Marie showed, also second derivative. Again, each configuration must be positive. Okay. So what happens is that now we can learn. So we have the ground truth is the Hermitz energy from quantum mechanics calculations, uses entropy. So basically this results. So we take the results, as you see, this is the red line, the DFT results at 20K, 60K. This is the physical temperature, but you can, of course, you can normalize it to any scale, and 120. And so then you see that you have two kind of double. You have double well, then double merge into one well, and then it become a single phase, so to speak. We call it. So this is the red data. Symbols are from the DFT calculations with the prediction. And the black line is learned from ZENN. As you can see, this is energy itself. It's almost perfect learned. And when we do DFT calculations, we have to take like 500 configurations because we take a supercell, which has a Gaussity of the configurations, we calculate all of them. And we get this data. And then after we learn it, right, then we can do the first derivative, get the pressure, the energy to volume, give the minus pressure. And then we can learn this, for a given pressure, we can learn how the volume changes. So this at given pressure, at low pressure, you can see that the volume increase, then started to change a little bit now, right? Increase much less here, or less here, okay? Less here. You see a little bit of change like a bending back here. Now if you increase pressure, you see the bend backs more. If you even increase even further, then increase to the critical point, this becomes infinite, negative infinity. Okay, so in this range, you see a negative sum expansion. Of course, we didn't put this kind of into constraints. Well, we don't have a model for it. But because of the ZENN model, we learn the configurations. And each configuration is stable, but it can predict the unstable because of this when it's entropy, P log P term there, and predict the critical point. And all this second derivative equals 0, that's the instability limit. Okay. So that means even though we don't put model into it, say it's stable or not, but after we learn the energy, we learn the configuration, we can predict where we have no data. So it has very nice extrapolation capability or the interpolation. Both of them works very well. Okay, so the idea is that we really cover a different type of data. So there's nothing very interesting. It's about temperature. For the physics, we know temperature, right? We know temperature, okay? And but however, what do we mean by temperature for data? I think that's as a new concept. Data has temperature, okay? I think that turned out to be very dramatic, as I will show this one. I think let's go back to when we're now, right?
Yeah, okay.
Yeah,
okay.
go ahead.
Yeah, I think we were confused. I thought you take out everything over there.
I want you to go to mathematics.
Yeah, okay. So anyway, so I think that is the one question about temperature. This is very good. The first one is you can think about the temperature could be is given, right? So like Zikui showed in material application or even the bifurcation temperature is given. Or you can also treat the temperature as a parameter like a semi-unit annealing, so then you can cool down the temperature, then you can have the convex. But I think when you give the data is more important, you need to learn the temperature, because this is temperature essentially tell you how many data resources you are coming from. So this is essentially the idea is you have the T1, T2, and the T3, T4. You have different set of temperature and tell you how many data set can be classified into the different resources. We built into the ZENN framework, and then eventually we can do this multi-classification regression or also the classification. So let me use the classification as one example to show you how you incorporate the temperature into the ZENN. Okay, so the first one is, again, we start with the cross entropy. You only have uniform temperature, uniform data set. You cannot not learn any difference heterogeneous data set through this, right? So we put everything in the cross entropy setup, like I said before. So you have two of these, right? So the first one is you have the TJ is a different temperature, is for different data. We have TJs, and so that means for different data point, we should have tell me what's the temperature. And moreover, for the E and the S, we have the different vectors. So for instance, E1 is K is the number of classification, how many labels, right? So if they go to CIFAR 10, K equals 10, CIFAR 100, K equals 100, and the M is the data set, the number of data points you have. So again, so if you put the S equals 0, so this is the recover to the cross entropy setup. Okay, so over here, so that means if you look at this the cross entropy loss function, you need given for any is a TJ, then you can compute E tilde and S tilde. But the question is, how can you infer TJ? So this is the way through the expectation maximization algorithm, EM algorithm. So you look at the probability, posterior probability of TJ, TI. So this is essentially for i's. So because the each data set, you should have T1 to TNT. So this is the number of temperature. We should know what's the posterior probability of the TI. So how you compute this, then you look at this one, you want to maximize this one, and each component we should have cross entropy, and the J and I is for J's data and I's temperature. And go through this, then you can find what's the temperature for each component. Each data point. Okay, let me use one example. So I think everybody use the class image. If you do the image classification, the benchmark setup should be either use the CIFAR 10 or CIFAR 100, right? So you can see the CIFAR 10, you have 10 classes of classification. You have the 60,000 total data. And if the CIFAR 100, you still have 60,000, but you have 100 classes. Okay, so this is one of the example. Through the ZENN, you can see this is the different this is our state-of-art model. Is VIT is for different parameter, different architecture, and you can see so what we should prescribe is the number of temperature we give. So for instance, so this is a different color, and the green one is to tell you, okay, if you give the 6 different temperature, and now you give the 5 temperature for red. So from here, you can see this is the error rate for the different test data set. You can see 5 temperature, you have the best. So that means, so this is the CIFAR 10 is from the 5 different resources. So this is the temperature, how we calibrate the temperature. We need to also learn the temperature through the data. So this is, you can see, so for the different temperature, is you learned a little bit different because this is the temperature is always relative. It sometimes depends on your model, but the whole point to tell you, at least to tell you how many resources you are coming from is consistent. From the different model, you can always see this from the 5 different resources is the best. Okay, and then we apply similar to apply to CIFAR 100. And so this is a different number of temperature. You can see it's two of the resources should be the best, and the black one, and you have the T1, the T2. This is how we compute. So then you may ask, okay, if the CIFAR 10 you have 5, but the CIFAR 100 only have 2, because you have the different data, right? So the CIFAR 100 only have 60,000. The CIFAR 10 is also 60,000. So they have same amount of data. So it's how you calibrate is really depends on how much data. If you have a very, very rich data set up, right? So then you can calibrate more details, right? That's why CIFAR 10 you have relative large data compared to CIFAR 100. So that's why you have a better classification for data resources, not the classification for the different class.
Well,
Okay.
Roy, I have a question here because I'm a little confused.
Sure.
I'm a lot confused actually. So you said the temperature reflects the heterogeneity in the data sources, but then why then your temperature here in the table? For this case, we have 2 temperatures. Why the temperature then depends on the architecture?
Yeah, because this is the temperature you should compute. There is no better way to compute, right? So this is we just kind of use some this is probably based on our algorithm is not very accurate. So we normally just kind of use a binary tree to discover what's the temperature. But I mean, so here this could be depends on how accurate for your algorithm of the computing temperature. I'm saying here this maybe is not very accurate, but the number of temperature is accurate. So you don't need to really concentrate on how much temperature, because the temperature is relative. There is no way you can define temperature exactly. So this is the T1 is we given. So if you only have one temperature, we given T1 equals 1. Okay, but the next one, how you compute is, I think it really depends on a lot of things. The temperature depends on your architecture, because we train the architecture, the different parameter of the model, and with the temperature together. So this
but if I have like let's say a CNN
sure.
and a vision transformer, right, somewhere in my system, and I do that,
then you will have much accurate temperature, because this is the model size is pretty small. So this is the kind of 22 billions of parameters, because we have to run on state-of-art model.
I see.
Yeah.
Okay. So you're saying that the value of the temperature is not important.
Yeah. But the number of temperature is more.
Yes, the temperature. Okay. But can you also explain here physically why in the CFAR 100 we only have, before we had 5 temperatures that mattered, and now we have 2, since this reflects the sources. Have you actually, can you go back and identify the sources of the data, or is it qualitative what you're saying?
Yeah, George, very good question. If you look at, we always have 60,000 for CFAR 10 and CFAR 100. CFAR 10, you have 10 classes, you have 6,000 image per class. But the CFAR 100, you have 600 image per class. I think that's if you look at the data density is much less, then you don't have enough data to calibrate. So then you just go very cost grade. You say, hey, this is the two groups should be enough. If you want to do the classification for the data resources more clearly, you should have more data.
I see. So if you had instead of 60,000, if you had 600,000,
yes,
then you would have 5 temperature also.
Yeah. This is what I saw.
Okay.
Yeah. So we confirm this on some synthetic data, but it's not.
Can you also comment on the value, like for example, on the relative value? The higher the temperature means what?
Higher temperature.
Do you want me to answer that, Unrei?
Yeah, please.
George, actually, I just typed it in the chat because DT asked that question.
Yeah.
So the temperature is really defined by the derivative of energy to entropy.
Right.
So that means if a high entropy, a high temperature, that means you change entropy a little bit and you change a lot. So what it means is that it means entropy becomes much important role when temperature goes higher. Make temperature higher.
So in terms of the data, what does it mean that the data is
more scattered, more scattered? Yeah. If the image has more depth, then temperature will be higher.
I see. Yeah. Okay, so the relative value of temperature also reflects. It has a meaning. Yes. That's the scattering of the data.
Yeah, it's not just number, it has some physical meaning, but I think what we mentioned is relative. We cannot so well define exactly what it for the data side, but maybe it can, I don't know. From the physical side, we can exactly define it.
Yeah.
But I'm pretty sure in the data we can define it too, but it just don't have enough experience yet, I think.
Right, but I think right now, if you want to have the real temperature value, so think about if you only have 2 values, and once you have to train separately, right? So right now we train everything with all the model parameters. That's the billions of trillions of model. But if you can fix the model parameter first, then say, hey, this is the best model we already have. Then you fine tune the temperature. Maybe you can get a consistent temperature here. So I don't know if my postdoc Shun is here, so probably you can try this.
ZQ, this is Suku here at Davis. I had a question and observation following up what Joe asked before. So when you go to like zero temperature, it's like where entropy has no role, right? Where it's purely energy controls everything. And then as you increase the temperature, there's more disorder, and therefore you get entropy plays a significant role. So what I see in your expression of this new form of where you add this S term to where I can think of it as like internal energy minus temperature times entropy, where basically you're finding out because similar things have been done when we did mesh-free approximations like 20 years ago, where you can think of if you have the internal energy term, if you think of it as a Gaussian, then you can look at it basically via the KL divergence. Basically, it becomes like a prior, is my observation, where you can think of as an initial guess, so to speak, for the distribution you're seeking. That is one observation, right? The second thing is that so your beta, which is the parameter right there, or like I think of beta as inverse temperature, which is basically when there's zero temperature, there's essentially a deterministic system. It's a deterministic system. So the one question I had related to what you were showing is what is your S? I mean, I have a P log P, right, which is the classical Shannon entropy minus P log P. So what is the S term that you introduce?
Yeah, so this is order fluctuation. Right? Yeah, so this is you can see the S actually is also corresponding to this internal entropy, right?
Yeah, so that's what. So do you take a specific form for S or what is S?
No, okay. So this is a good question. So from here, you only take the S and the E are your unknowns. You should be able to solve S and the E through this minimization problem or maximization problem, constraint optimization. You cannot prescribe any S.
So S is itself an unknown.
Yes, that's why it's from here you can see this is you solve for PK in terms of EK and SK, but I don't know what's the EK and SK. We want to use a neural network to parameterize the EK and SK.
So probably just go back to the previous slide because I can tell you why I'm asking the question. Because typically, if you just do Shannon entropy maximization, right? So you only have the black term, not the red term. And then you optimize subject to some constraints, right? You have summation is 1, but then you have the first order moment, which is C1, the second order, which is C2, and so on, right?
No, you don't have second order. You only have first order.
Yeah, but only first order. But I'm saying that in general, basically, Shannon entropy is a way to provide inductive inference, right? When you have severely underdetermined systems and you have constraints, the question is, what is the solution I pick? And then you say, okay, I maximize entropy, right? That is the basic rationale. But so I was trying to relate here is probably a bit different because here you're saying EK and SK itself are not known, right?
Yeah, so this is essentially how you define the energy, right? So I think that maybe that's the Zikui. This is the whole idea is from here is you
go to slide 12. When we go to slide 12.
Okay.
Yeah, this is one. Kuma, right? Kuma. Yeah. This is really one. So you look at this one. The two S are the same. Okay. The total entropy of the system. You can do P log P. Use Gibbs Shannon, but you have to go down to so low scale.
Right.
Your computer has no entropy. But you cannot go that low scale. You go to intermediate scale. And the intermediate scale, each computer has entropy inside.
So can you correlate this phase? Suppose I'm tossing a dice, right? And I'm just tossing a dice, like it has 6 faces.
Okay.
Right? So then I know, okay, in a normal sense, I'll just say, okay, if I just know the summation is 1, and I know the expected value of the first moment, right, is some value.
Yeah.
Then based on that, I can just apply Shannon entropy and find out what is the most likely distribution.
That's right.
Right?
Exactly.
But now, can you tell me something about the dice that makes SK required? Right?
So what it means is that, so dice is suppose 1 to 6, right?
Yes.
1 to 6. But actually, each 1, 2, 3, 4, 5, 6 itself is not equivalent.
Exactly. Okay.
Because you have one side have 1 dot, another 5 dots. They are intrinsically different.
Yeah, but doesn't that come out if you suppose you tell me the first moment as some value, right? That it because if you give a dice and you say the first moment value is 3.5, then I know it's unbiased. But if you tell me the first moment is very high, much higher, then I know that the probability of 6 is higher, right?
That's a great question. That's a good question. What it means is that in that experiment, the SK, all SKs are very similar. So it doesn't matter.
Yeah, okay.
I think you can think about you have 2 different dice, right? So you 2 different dice, you have 2 different bells. So this is essentially how we collaborate with Zikui is we always use this example. Okay, you have a coin, right? So these coins are different. So then how can you guarantee that's the one half because the weights, everything is different. How can you quantify the difference? This will go to the SK.
Right. Yeah. So in some sense, you have many coins or many dice you're tossing.
Yeah.
And they're not exactly the same.
Exactly.
But if you only have 1 coin, so that means you only have 1 data set. You don't need the SK, right?
Yeah.
Let's go to the entropy. But right now I say, okay, I have some coin, you have some coin. Okay, let's get some data. Then you want to merge this data together.
Right.
SK cannot.
So that's what you're saying. So you want to sort of quantify the micro state situation, right?
Exactly.
I think it makes a lot of sense because if you flip euros and if you flip quarters, dollars, it's different.
Sure. That's right. That's right. That's absolutely, George.
Okay. Okay.
Okay, since the noon is going to be at 11 o'clock. So
yeah. Thanks a lot. Yeah.
Right. So let me put more. So this is we also apply to the more data set, right? So this is I talk with my collaborator in large language models. They are doing this is a text data set, right? So one is the BBC News and one is the AG News. So they also do the classification. So this classification is different topics. You can see the 5 topics: business, entertainment, politics, sport, and tech. And the input is your whole newsletter. Then you want to do the classification. So this is use a large language model. We cannot really find all the large language model. We just fine tune, right? So you can use the fine tune incorporate with then so you can have the similar thing. So if you do the BBC News, then you only have two data sets is enough, right? So you can find the T1 and the T2. And if you go to the AG News, you need 4 data sets. So this, if you don't incorporate the entropy, you just use cross entropy, which is CE, is blue one. You can see this is a 6% of prediction error. So, but if you use the cross entropy, you can only have 2%. Okay, so that's why when you incorporate the different data set, this is the whole point. You do need SK. So that's if you need SK, you need a new formulation, how you compute the probability and how you quantify the temperature. So that's I think I pass this to Zhang Long, since Zhang Long can talk about more applied for geoscience with cross entropy. Yeah.
Thank you, Henry.
Yeah.
Hi all. I'm glad to join here. I think I'm kind of an outliner here about the topic I'm talking about. I mean, the application domain. But let me share my screen. Share my screen. Okay. Can you see my screen, everyone?
It's coming up.
Okay.
Yeah, we can see it. Can you go to the slideshow, please?
Yeah. Right.
Thank you.
Yeah. So greetings from San Francisco. I'm attending another conference here, a geography conference. Good to see everyone. And I have several minutes to quickly go through this. If I cannot finish before I have to leave, and Zikui can continue finish that since Zikui has been working on this. So the title that I want to talk about is just like we try to introduce or to come up with some dynamics inspired explainable geospatial AI. Is also based on entropy to uncover the regime, change and in the heterogeneous spatial systems here. And this paper is still working. We are going to submit soon. But this is the motivation of the ZENN here. Oh, this is, we call it ZENN, okay? Entropy enhanced GNN. And so why we are working on this? I think one of the reasons that you think about the spatial analysis or spatial modeling and modeling the spatial heterogeneity. We talk about heterogeneity again. Not data, it's still kind of data heterogeneity, but in a spatial system. And also related to critical transitions is remain a major challenge in our domain. And if you think about some example here, for example, when you think about this, if you want to model the housing prices or model the mental health at the county level across the US. And then when we do this kind of modeling, typically we need to collect a data set, for example, at the county level. Let's use the housing data set example in the city. And then if we want to predict the house price, the home price, based on the homes, for example, the lot size, the homes, the year built, the number of bedrooms, and then the grid, right? So all this information put together, and then you are able to build a model to predict. If you give a new location of a house, the parameter like number of bedroom size and the lot size, and then you are able to predict the price, the home price here. So this is a typical problem in the geographic science in our spatial, consider the spatial system, because the location is very important in predicting the home location. This is something in predicting the home price. So this is a common sense, the same size of house in the downtown in the big city and compared to the suburb or in a rural area, totally different, right? So this we call the spatial heterogeneity. The same factor, think about the same kind of like home, the square feet of a home, is playing a different role in different locations. So traditionally, we have in our domain, we have been using, for example, geographically weighted regression. It's kind of a regression analysis, but consider the location of the observation. All right. You think about instead of doing traditional regression, but in the GWR, which is a traditional way to do that, and we take local observation as an analysis unit, like a neighborhood. And then we do a regression. And then for another location, you do another kind of a local regression. And finally, you have all those regression done, and then you have kind of to capture the varying spatial relationships for different factors across the entire study area. So it's a kind of a local model. And so it only works in the linear function forms, which is treat linear relationships. And then using GEI or deep learning, deep learning models like random forest or DNN, they can also do the prediction of this housing prices, for example. But again, when we do this, the result you get, it purely is a black box representation, of this. If you get higher R square or get higher prediction, but still you don't know what happened inside in this black box. So the interpretability is low. And sometimes it's very important for us to know that not only you get a higher R square prediction performance, but also explain why, for example, for the housing, why a specific factor is mattering more in one location compared to the other location. The same thing for the public health, for example, when you look at the mental health issues, studies here, the factor here affecting those kind of outcome is more important than just for prediction. So that's the motivates the study of this introduce a thermodynamics inspired explainable GUI framework based on the entropy, based on the ZENN. We call it ZENN here, or based on graph neural network. So just a very quick overview of the ZENN. So we treat the spatial outcomes, which is think about observations, spatial observation, think about housing price. If you the study you are doing, predict the housing price, or better understand the mental health distribution at the county level across the US, or look at the PM 2.5, like the air pollution, across the study area. So those are the spatial outcomes. We treat that as emergent from the computation between the disorder inducing burden, here is E, and order maintaining capacity, which is S here. Summarized through the latent free energy function, this is where the ZENN basically formula here. And then I generate this figure using a ChatGPT, Gemini, I think. And it's very nicely summarized overall concept here. So they are competing all these factors together and then finally produce a free energy surface. That surface will be the outcome. So that predict outcome here. So again, I have the explanation of the T here. What this T is meaning here. It's a learnable parameter. It's not the actual temperature T, but it's more from the data science, from the as Wenri and Zuki already explained, but applied to this domain that we are talking about here. So the graph, the neural network we are using here is graph neural network because when we do the spatial system prediction or spatial regression or modeling, we have to consider the location. And the location here is about the neighboring location. Like if you have, for example, you think about when you want to buy a house or selling a house, right? How the appraiser, the appraisal appraise the house price, the home price. They are based on the neighboring locations of the house. Like in your neighborhood, if there are 5 houses sold at the different prices, and then your price will be estimated based on the neighboring, right? So neighboring location is very important thing to consider in any spatial analysis. That's why the graph here, or you can think about the graph node, and the node in the graph in our study here will be the specific location. You think about the specific home location, a specific like a county or sensor tract or zip code or any other observations in the spatial system that had a location, right? That's why we use graph to encode this spatial location, spatial information into here. We build a graph aware spatial context. We use GN here, and then those graph will be integrated into this Zentropy or Zen style function here, because to produce the free energy as I just mentioned before. And then finally, there's a gating network here, and to learn these parameters And then finally, we have this output here. Of course, the prediction, we use R-square or other like RMSE to evaluate the performance. And most importantly, I want to say here that we produced explainable surfaces that can explain which parameter, like the bedroom, number of bedrooms or the lot size, are more important in one location than the other. And those are something is missing if we are only using a deep learning model to model these relationships here. Even though there are some, post diagnostics function like the shape to explain those, but what we are doing here is a traditional. It's just like you have those diagnostics directly output from the model. It's not like a post diagnostics after you get this model result here. So that's the idea here. I'm going to show you just have time probably to show one. We use some three simulation data set and also three empirical data set to validate this new framework here. So the result you are seeing here is one of the simulation data set, which is showing we simulated 5 variables. You think about the linear regression or the regression analysis. You have 5 axes and 1 y, right, outcome. And then this 5 variable is predictors to impacting those outcome here. And they have the relationship between each 5 variable with the y here is showing here. It's not a linear relationship. And then in the panel B here, you can see this each point here you can think about is one observation, one location. All right, the location here is matter. This is basically a true location, a spatial location here. And those are the point here you see. This is the two regions, two resumes here. It's like, I don't have time to explain that more, but the resume here is more like spatial cluster. Like in one area, all those relationship spatial system is functioning in a similar way. And then in the other area, they are functioning in a different kind of style. And the relationship is hold kind of similar in one resume. So in this simulation that we have the two resumes here, we have 3, you can see from the shape here. And then on the right side here, you can see this is a predicted one. It's very, very close to the 2. And then we have a gating uncertainty, which is based on the entropy, normalized entropy here. You can see the high entropy, which is all occurs in this in the boundary. This is like you can identify this transition boundary here spatially based on the entropy of the entropy. And then following, you can see the free energy, free energy F here is indicating the outcome, which is the Y variable. And then the predicted free energy, which is the predict the Y here. And then based on that, we can calculate the R square. And also this is the burden and the capacity, or we can have this map to show spatially how this look different. And then we have other kind of diagnostic here. And this D here shows the prediction performance, just without looking any explanation, explainability, but look at the R square and the entropy based graph, GN performed the best in this simulation set here. And then also you can see it uncover this when we look at this partial derivative of this free energy, the F, dF over dx here. You can see the true, this is the true, impact. Think about the coefficient, local coefficient, or local impact of a specific factor, or like x1, x2, to the final outcome here. And then this is the first column here. You can see in the E panel. This is the true, and then the second panel is the predicted. Or this is like the model uncovered relationship, which is again is very similar compared to the true relationship here. So that's I think this is from the simulation set that we get here. We feel that it's working very well to achieve or to uncover the complex spatial system in terms of different factors, how those are impacting this final outcome, and based on the burden capacity computation, and to produce the final energy surface. I think Zhihui, if you are able to take over the field slides, since you have
okay, I can do that.
Yeah, very familiar with this. We have been discussing all the time.
I can do that.
Right?
Okay.
Yeah, I have to leave. Sorry, to another meeting. I'm happy to talk to you later about this anything. All right, thank you. Thank you for the chance. Yeah.
I will continue, and this manuscript we have revised 3 times. I hope it's finished very soon. And this graph, ZENN showed here is showing the graph presentation, but also putting the value here. For the housing one, you can see a different model. GWR is the conventional model used, and random forest is the deep model, and the GM is a standard model too. And this is ZENN. So you can see that there are two for the random sample, random cross-validation, and the spatial cross-validation. You can see it's overperformed all of them. Again, ZENN mentioned two things. One is GN, is about the neighboring effects. Another one is a global effect. Is this regime. So you divide the whole system into big regimes, and the regime has effect on each node. So two added together, and they affect the performance. This is for the housing price. This is for the mental health. Again, it's a GWR. This is actually not bad, right? Not bad this one, but this two, and it's also Zhang basically outperform it. And the PINN 2.5 is actually a very tough one, because PINN 2.5 is affected by the wildfire very dramatically, so it's very time dependent. So we didn't do all the time dependent this time, but we take a 1 month of data to the analysis. Again, you can see that the random forest is usually pretty good, but it's very heavy. But ZENN just they outperform again all of these models for this one. And then another one for mental health. Again, the graph. These are the data points. Okay, data points, and these are the graph again. You can see that for the whole country, and it's remarkable performance with that. A paper will come out very soon. Again, it's this. You have three terms again, right? You have energy, you have energy, and entropy. Okay. Of course, the mathematics is different. Mathematics is different than what when represented for that kind of classification, because it has GN for the local, and this region for the global effect. These two facts combined together make much better progress. And even very important thing ZENN mentioned is that during the analysis, we will know which factor has large impact. You don't have to do the post-analysis. It come out during the analysis. All right, so let's give as conclusion is that the entropy is basically entropy. As Kuma asked the question that you have P log P. If you sample enough, if you make all the samples, P log P is sufficient. But usually you don't have so much data in depth. So you do the intermediate configurations. When you do the intermediate configurations, you would have, each configuration will have entropy. So that entropy could be very significant. For example, when you get a physical system, the liquid. For the liquid, we think P log P should be huge, right? No, the first term actually is dominant. This phonon is more dominant. But so the entropy really put them together. So as ZENN mentioned, sometimes it changes. Sometimes the second term is more important. Sometimes the first term is important. So it's system dependent or the situation dependent. So two terms both could be important. Sometimes one is more important than another. So that means we can really look at the intrinsic entropy as SK plays an extremely important role and to govern the performance of the system. And then based on the entropy, we developed a ZENN. We showed it for the classifications. Temperature is a very, very, very important concept here. As I mentioned, temperature is energy to entropy derivative. Okay, so it's how much entropy affects energy. Okay, there are two terms. Remember, as ZENN mentioned, one is burden, one is capacity. So that governs how the system performs. And we also do energy landscape, that's regression, so it's classification, regression, and the physical properties. And we understand structure, the data. The structure data is not a post-analysis. It's in the process you get to understand the underlying structure, which one's important. And we now apply to the geography data, and we are applying to many other data. One of them is Alzheimer's disease. Will come out very soon, hopefully this paper. Is that you can look at the heterogeneous data, find the underlying features and performance. Okay, with that one, I want to thank you. Thank George to give us the opportunity to present our work here. Looking forward for your questions and also for collaborations. Thank you.
Thank you, Professor Liu. Thank you, Professor Hao and Professor Lee. We can ask more questions to the others. So I have a question, Professor Liu. So for the classification problem in CIFAR 100, if I understood correctly, you used 200 vision transformers as the architecture because there are 100 classes, and for each class being a configuration, you need one transformer that predicts the E and another transformer that predicts the S. So you use 200 networks.
Yes, I think, yeah, that's right. That's right.
How many parameters were there when you used 200 transformers?
It's in our supplement document.
All right, sure.
So we have all the number of parameters here. But if you look at the comparison diagram, it's actually very interesting. Is that we can use a smaller model, have the same performance as larger model.
Right. You make the model smaller so that the total number of parameters remains more or less the same. Understood.
Yeah. Right. It's the same as the large model.
Understood. Perfect. Thank you. It is a really interesting talk.
Yeah, hello, Professor. Great talk. Even I had a question building on top of, I think, the primary pipeline that you were talking about, right? Where you were trying to predict E and S. You have like individual networks, K networks, where each one of them predicts E and S, and then you try to compute the probability, right? So like, could you explain how is the loss formulation done? I didn't quite understand the KL divergence part that you were talking about, because like, how do you have a closed form expression for E or S? That's one question. And then how do these problems translate where you're probably using it for some particle dynamics solver where your K becomes extremely large? Like in classification problem, you're probably working with like 10 classes or 100 classes. If you're going for some other simulation where you're having several coarse-grained particles, then is that a limitation, or how does this approach mitigate that?
That's a great question. Let me just share my screen again. Maybe I should not stop sharing. Let's keep sharing. That's a great question. It actually goes back to what we talk about here. Okay. So your question actually is on left side. If the system becomes bigger, you need a lot more configuration to put them together. However, you can go to coarse graining here. So this entropy is fantastic in coarse graining. You don't have to take that many configurations because you put all unknowns inside of this variable.
Right.
So you learn the SK. SK capture everything below.
Okay. But so learning SK will become more complicated, right? Because you're trying to like cluster more of them. So the entropy increases for each of these coarse-grained intermediate configurations. So learning SK might become a more difficult task then.
Exactly. So in that way, your model actually very simple. Instead of taking millions, billions here, maybe you only take like 1,000.
So was this the part where Professor Lee used the graph network, to message passing graph network to accumulate information from neighboring nodes to the
That's right. So see, that's exactly how the geometry worked so nicely. So you divide this nodes first, right? But you want to put all artifacts into consideration, the interaction will be very complex. But now you look at the regions, you learn how that region affects that node by the two variables, E and S. So you significantly coarse-grain the bigger problem. Okay, that's the first one. Second one, what's the first question again? First question is about the loss function. Yeah, the loss function is not this one. Let's see what's the loss function. Okay, here. All right. So this is one. You first we have to put temperature into it, right? We have to put temperature into it. Okay. So we have to put entropy into it. So that means this is you want to maximize this entropy. Previously, we just do the P log P. We have the two terms, right? So now we have another term, so Lagrange has one more term, basically. Does that make sense? But when we calculate the entropy, okay, this is how we calculate the cost entropy here. So instead of while log P, where we calculate this one. Okay.
Right.
You calculate you don't learn the probability. You calculate the probability. Of course, you still learn. You learn E and S. You calculate the probability.
Okay.
So that's where you have the S into the loss function.
I see. I think in the previous slide where you had the KL divergence computed, right?
This one.
Yeah. Or probably before that. I think 2 slides before that. Yeah, slide 20. Yeah. So
this is the standard one, right?
Right.
Yeah. But you see,
please go ahead.
This is standard one, right? Standard one here. Okay, so basically implement this one inside here. Now we have the E and S separate.
Right.
Previously we basically only have this first term, not second term.
Okay. All right. Yeah. Thank you.
Do we have any more questions for the speaker?
No, I just had a short follow-up.
Yes, ma'am.
Yeah. So in terms of the temperature, right? You have only discrete values of the temperature as the output?
Yes, temperature is discrete.
And how do you know how many discrete values you'll get out?
We don't.
You don't know, right?
We don't.
So, but is it possible to think of it as a continuous variable field?
Yeah, you can actually because temperature is this is all digitized in our case. Well, we divide the system into configuration. That's a number, the integer number. Okay, how many configurations we have. But that, as I showed in this slide, the configuration is really arbitrary. You can take any number of configurations, but it captures a feature of your system. So that's how to do the cross graining. That's the first one. You get configurations. Then this data in different configurations, the data have different temperatures. Okay, but the temperature is across the board. It's not just one configuration. It's across the whole system. That means I have so many data. It looks like they belong to 3 temperatures.
Okay.
So you see, it's like 2 levels. You have 3 temperatures. You have 5 configurations.
Okay.
So configuration is horizontal, temperature is vertical.
Mm-hmm. Mm-hmm.
Yeah. Of course, you cut more. Something is not good because cut more does. If you don't capture the feature of it, more does not mean good, better, right?
Because I saw in the last term you have a summation tj, right? In your last term, so I figured it was discrete, right?
Is that slide 20, right?
No, the one you just showed before some time back.
Oh, here.
No, afterwards probably. Where you had one last term where I saw a tj.
Oh, okay.
Yeah,
this
anyway,
one.
it's okay. I mean,
this one.
Yeah, maybe that. Yeah.
Yeah.
So here you have a sum of. So I was wondering that TJs are not known, right? The above. Yeah, that there. Yeah.
SM?
No. Yeah, the TJ is there, right?
Oh yeah, it's learned. It's learned.
Okay.
It's learned.
Okay.
Yeah.
But then what is the t that you input to the model in that case? Your input is x and t, right? To your model.
Yeah, it's your input data of the model. It's you don't have temperature input. It's not in input. Temperature is we learn. It's latent parameter.
Okay. Can you go to the slide where you had the different transformers arranged, like K configurations?
This one?
No, before that, where you had the architecture.
Oh, architecture. Okay. This one.
Yes, so you see on the input you see x comma t over there. So that is why I was confused. I
this
thought
one,
the
right?
t was. Let me just try to annotate it.
Right
so
on top.
over here.
Okay.
So you see there's an x and a t over here. So temperature.
Yeah.
So
this t is that because when you start to learn, you have to give. You see it's 1 t or 2 t, right? You say I want to give 1 t. That means just one temperature. I said I'll give 2 t. So I have 2 temperature, but you don't know the temperature.
Right. So how do you decide, give attribute? Let's say you have 100 images of cats. How do you assign the temperature for each of these 100 cats?
Oh, so we don't. We just run. We assign randomly.
Okay. But then in the below you computed like
exactly. Then you compute say, okay, this one belongs to that one. This belongs to this one.
Okay.
Yeah.
Okay. Sorry, I interrupted, Professor Sugu. Yeah, go ahead. Yeah.
Thanks.
So the one of the very interesting. We actually we discussed, right? What temperature of data, right? That's what do you mean by the data has temperature? Okay. But for the definition, we know it. The temperature is energy to entropy derivative. We have energy, have entropy, it will derivative with temperature. So it's basically how much the entropy affects energy from data point of view, right? That means some of the data entropy affects more, some affects less. So you start from the category to categorize the data. So, okay, some data have high temperature because they affect energy more. Some of data affects energy less, so it's a low temperature.
Okay.
So it's because of there's S in it. That's of course, in principle, you can use the cos entropy. You can do that too. Cos entropy, you can do that too. But it doesn't matter because if you don't separate in individual temperature, the temperature effect just go to E. That was Kumar asked the question. So Kumar asked the question because if you don't separate to the S, you don't have if you don't have this term, you can just combine E and E minus TS in one term. Right? So you have to separate each configuration has different entropy, and then that becomes important.
I think just a short note. It'll be interesting to see what did you finally get for the expressions for SK and EK, right? What was it finally? How do you interpret that?
Interpret basically means that what it means is that suppose we have now if you look at the data, we have like we have 5 temperature, right? 5 temperature is the lowest one. So that means take the 60,000 data, they belong to 5 temperatures. That means for the different groups, their energy to entropy derivative has that kind of value. That's what it means. That means this group of data, image, their energy increase much more by entropy change. Okay, that means entropy change a little bit, energy change a lot. That means basically what it means is that means this data has much more noise, so to speak. You think noise is entropy, right? But entropy and temperature coupled together gives energy. Yeah. So entropy itself is not energy. You have the times temperature gives the energy. Yeah. So that's why separately learn them will give the temperature effect.
Yeah. Okay. Thanks.
Thank you, Professor Sugu. I think Guru asked a question in the chat. Even for cipher or text dataset, can you evaluate temperature derivative and find a critical point in principle?
Oh, is that in the
chat?
In chat. Let me have a look.
Hi, thank you for the great talk. What I'm asking is a kind of stupid question.
Oh, that's actually that's a good question. We can do that. We can can evaluate the critical the temperature derivative, critical point. Exactly. So in this diagram here, is that's exactly the one we did. Where did you take this one? So this is the critical point.
But this is the material science program.
We didn't do for the data. We could do it. We haven't done the data. Yeah. So actually, what's the name of this question? The person? Let me just check it again.
Suguru.
Suguru, yes.
Suguru. So this is actually critical. This is actually my new proposal now. It's called AI safety. So what it means is that during the evaluation, when I see the data, I can evaluate the first and second derivative. Okay. When the second derivative starts to become smaller, I need to start getting worried. Okay, and the first derivative, I can control the first derivative, tells the system where it should go. I can control the input variable. System go this direction because I want a high driving force. That's first derivative. And then at the same time, I monitor the second derivative. Same time, it's simultaneous when doing learning. Then you say, oh, no, my second derivative now become less positive now. So I need to worry about myself. I'm going to do the crash point, you know. Exactly, that's exactly our new proposal. It's called a self-containment, internal containment. Thank you. That's a good question.
Thank you.
Thank you, Professor Liu, Professor Lee, and Professor Hao for taking your time and presenting ZENN. It was very interesting. And with that, I would like to close this week's Crunch seminar. And thank you, everyone, for attending the seminar. Have a nice weekend.
Thank you. Thank you.